Thank you very much for the kind introduction. Joanna, Daniel, thank you for the invitation. I'm glad to be here. And I'm also happy to be to the introductory talk. So that means I can talk about a little bit about the history, about studies we have done a couple of years ago, and give a little bit of broad introduction also to the students maybe who are joining. And then I'm looking forward to the speakers following who give probably more results on the last few years. So I'm based now in Winterthur. I want to acknowledge like my group members who are like helping me starting up my group already for 2 years. We're also looking for PhD students still, and the funding from SNF and from PRC is also acknowledged here already. Okay, what do I want to talk about? I want to give a brief introduction to the perovskites and stability measurements. Then I want to motivate a little bit this work to be called real world. So there must be a kind of reason why we need to distinguish or why we want to distinguish at least maybe for the state of the art between lab tests and real world tests. And then I will show one study which we conducted at EPFL a couple of years ago, where we really looked into real world daily profiles in the lab and with some final remarks. The material we're talking about, these are the metal halide perovskites. That's a specialized conference, so I don't need to introduce them in detail. Well, it's not only a single material. Now, the perovskite is a crystal structure. It's ABX3. Here is a cubic representative. And online, I think you cannot see my pointer anyway. So probably not. It doesn't make too much sense to use it too much. But what you can do is you can form different lead or also lead-free. I guess we'll hear about them later. But for example, lead halide hybrid and also like fully inorganic perovskites can use, for example, cesium lead iodide. And that's not the only point. Of course, you can start mixing them, you can alloy them. You can do what people call like compositional engineering. This helps you a lot to do stabilization of the phases, because it's not given that when you mix those and try to make this ABX3 compound that it will end up in a perovskite. Other phases which are usually not very useful for the perovskites. But you can have this phase stabilization, and of course, you can tune the electronics mainly when you change the B and the X side. So when you tune, for example, iodine bromide, you can tune the band gap and the whole visible range from UV to infrared. You should take also the tin. And that's very useful both for solar cells and for other electronic devices. Okay, here is a kind of little introductory slide on the optoelectronic plus ionic properties of this material. So this is a semiconductor. So we have like the common properties that we know. We have a band gap, as I already kind of mentioned, that we can tune it. And this is important, of course, to absorb, emit light in a way that it can be used for optoelectronic devices. We have charge transport. Electrons and holes are rather mobile. I can already put this in. People always say these high mobilities, but always it needs to be put into perspective, like for thin film material, especially if you refer to organics, mobilities are rather high, but if you refer to inorganic materials, they are still low. So that's why we tend to make most of the devices still in thin film, nanocrystalline film. Of course, we try to make also single crystals, but then also usually we try to make them in the Z dimension as thin as possible. We don't want to millimeter devices. Okay, then what you can do with silicon. And what is additionally important in this material is that we have, and that's why probably also one major motivation for this workshop, now we have like ionic charge carriers, if you want to call them like this. So in our lattice, here represented like this, you will have defects. Now they are thermodynamically unavoidable. They could especially then also result from plane boundaries, surfaces, etc. For example, here a halide could be missing. That would then be, this goes in as I minus, for example. Then you would have your positive charge vacancy. And this vacancy then you apply an electric field, or then you cause some kind of gradient, which can be in the material. and move much slower than the electronic charge carriers, but move in ranges. Now, there is like a lot discussed how fast they can move, but they move with better response times in the milliseconds, seconds, and up to longer times. And very interesting is the defect tolerance. That's the last point I want to mention here. Because we have anti-bonding orbitals, like for the quantity orbitals, like the valence band, for example, that's like uncommon if you compare to covalently bound semiconductors. They usually form shallow states, so you don't get so many defect states in the middle of your band gap, deep inside, because those are very detrimental and they capture charges easily, they recombine on radiatively. Your solar cell, your LED is not very efficient. Another interesting point is that the whole material, one could say, is rather dynamic. For example, the formation energy of the perovskite itself is rather very low. And this helps a lot to basically do self-healing. It's possible that these defects are kind of dynamically generated, but they can also rather easily heal. Because maybe it's easier to heal the perovskite than forming defects. Okay, and of course we put this material into devices, so that's only like the story about the material. When you talk about stability, very often the limiting processes are not the perovskite at first place, but mainly the interfaces of the charge transport layers. You need these layers. This is a cross-section taken by an electron microscope so that you can see probably almost all of you know how these devices look like. That's an NIP one. I can directly continue here. We use these charge transport layers electronically to make sure that contacts are selected. So that the titania in our case only accepts the electrons, makes sure that the holes are blocked. We also want to avoid here a combination that usually still is happening. The same here on the hole transport layer side, vice versa for the holes. Now I want to come to the stability. And I start with this golden triangle. Yeah, the one I mentioned already, commercialization. So we have this triangle where solar cells should be not extremely expensive for a simple technology that looks good, not so much energy intensive either. That's also important if you want to work on solar cell technology that will be employed soon by climate change. Of course, they need to be efficient, otherwise it doesn't make sense. And they should live for some time. Regarding efficiency, I think no discussion needed. More than 25% have been reached. It's this kind of, on this chart, they have all technologies, like these points here, going up here. Now it gets more and more difficult to increase it further because the theoretical limit is around 30% of the limit. There are obviously some practical issues to approach it. So how about the stability? The stability became important already quite some years ago, and now it is very common that in publications you find always such a graph, like we have here from Michael Saliba's triple cation paper from 2016. Now you see there was this modification adding the cesium device kept here at maximum power point, became more stable than the reference. And this is just a very recent work where you see still kind of the same graphs. The reference device increases quickly, and the kind of modified one. This is with colleagues. I helped them, Professor Jenny Yi, Tsinghua University. They developed kind of way out of the perovskite vacuum plus solution process, adding a bit of slag chloride, which makes it spread. So just to show you here, like what we see like in applications nowadays. Of course, others can do better than those where I'm involved. This is like one example from last year where the solar cells made by the Kaustin Stefan de Wolf, now they passed the test when they had the modification. This time really again it's about interface. They put here some I think 2D layer on top, and they get much more stable devices, around 1,000 hours they are measuring. But you see here the maximum power point tracking. So you see like there is variations. So one can probably say these devices are more or less unstable. This holds, in my opinion, still for the best devices. There are even like better ones where stability is even higher. This I think just came out 1 or 2 weeks ago. in science from Jan Fayan and Ted Sargent. And they are showing here, like this time, they were using this kind of fluid space, I think it is, to activate the perovskite surface. And they report here this kind of efficiency curve. Again, not ideally stable, but refer to the initial efficiency, and it kind of even increased. And you have more of this. This one from last year. This is from Kanatsides and Mohite. They really have here like impressive value now, and here an absolute value, 24% efficiency. Again, is the 3D, 2D perovskite approach. And they report already now this T99 hour. Now that means, in principle, I don't know how many devices are measured here, but in principle, during their measurement, this was rather stable. There are still some fluctuations. I don't know whether it's experiment or whether it's still the device. So nevertheless, devices are more or less unstable. You see, they also used already like elevated temperatures here. Okay, so we have these tests. We saw them, they are now mainly conducted on the maximum power point, often a little bit under elevated temperatures. There are different like conditions regarding atmosphere and so on. So the question is, why do we want to discuss real world kind of separately? And the motivation is here. Now, Giovanna had already a much nicer photograph at the beginning. But the life of the solar cell is, of course, not standard reporting conditions. It is not like 1,000 hours, like one sun illumination constantly. We have fluctuations in temperature and illumination intensity, also in the spectrum. We have changed weather conditions, and we have also changed voltages the solar cells use. On the one hand, because light intensity changes. On the other hand, maybe there is no demand and current at some point, then the device has to be at open circuit, and there is no other way for it, or when partial shading occurs. This I will briefly mention later. Okay, now to give a few examples now why always having the perspective on the, let's call it real world conditions is important. And one example is, for example, here, that's not about the efficiency, not about stability, but about the efficiency. This is when you make tandem cells with silicon. You want to match the currents, and the silicon band gap is very much fixed. So you have to tune the perovskite band gap to get the optimum distribution of harvested photons from the sun to get current match and then reach the highest efficiencies. And people usually do this, of course, under the solar simulator at 25 degrees in the lab, and they come up with the condition. You can just use the left bottom, right bottom graph, number F. Labeled F for the online audience, and look at this one. Usually you say we need around maybe 1.7 electron volt band gap for the perovskite. But what they found here, because they are also an house group, they are interested in hot climates. They see that actually, because the band gap is a little bit the temperature mainly of the silicon, they found, for example, that if you operate it at 60 degrees, maybe 1.68 electron volt maximum. And this is, of course, good news, especially in this case, because of the phase application of higher band perovskites, which I also will comment on very briefly. Another study is like we did quite some time ago. Of course, when you have higher temperatures, many processes that are thermally activated occur much faster. And one example was, for example, this one, that we have metal diffusion from the gold electrodes through the whole transport layer. If you don't use different methods to avoid it. For example, you just put gold on spiral. It's happening, accelerated by temperature, and at the end, you get like you lose efficiency very quickly. And you can also prove this by measuring very sensitively the quantum efficiency of the solar cell versus your energy. This is where the perovskite absorbs on the right side, about 1.6 electron volt. And then on the left side, we see these additional tail states that are generated when gold enters the perovskite. So in this case, the perovskite is not defect tolerant with gold, but this gold really leads to degradation, both in the open circuit voltage and also we start losing current. And one more example for different operation conditions. It's also early results on NIP devices, the state-of-the-art devices at EPFL in around 5 years ago. And also there we could see that dependent on at which voltage you operate this device, you get differently fast degradation. In this case, open circuit was the worst. One can try to explain it by saying that at open circuit, all the charge protein and charge carriers have to recombine in the device, and charge carrier density is highest, much higher than at maximum power point. At short circuit, where you harvest the charge. And there are more charges available. That means perovskite is more prone to like chemical reactions, which can then cause degradation. There are similar results, of course, in the literature. There are also, I think, other reports where maybe one or the other point is more or less severe. Here, maximum power point was actually the kind of most moderate, because short circuit, you have a rather strong electric field still in the device. Actively short circuiting it, then you can trigger, for example, more of this ionic migration. And you see also what happened here, but this I will comment on in a second. As last point, I have here this dependence. So this is not about stability, and we shouldn't call here any of these points degradation. This is just the efficiency versus light intensity and versus temperature, because the physics of the device dictates also how it behaves. And this is not about reversible degradation or something. Often I read, or sometimes I read this because I don't like it. It is just that there's a temperature dependence, for example, of the open circuit voltage, and increase the temperature, the has to go down thermodynamically. The same thing happens when you go to lower light intensities. The efficiency decreases also mainly because of the open circuit voltage. When you compare perovskite on the right, the silicon solar cell on the left, you can see, and I think this holds still for nowadays devices to some extent, that the temperature dependence, for example, of the perovskite, here, this is maybe typical operation temperatures one might expect, is much less pronounced compared to silicon. And this is in this case, of course, because there are processes like, for example, slight increases in fill factor because of enhanced charge transport, and mainly in the charge transport, like for example, organic materials, spiral, compensates a little bit the VOC decrease. If you make a highly efficient perovskite solar cell 25%, I would expect that it will go more and more, it has to go more and more behavior. So there's this temperature dependence. Okay, but that's still probably not enough to really make this workshop now on the real world behavior. One important point is missing. Not only we have fluctuations here in the conditions, but we have fluctuations in the perovskite solar cell itself. Perovskite solar cells, I say they're kind of volatile. And this is, for example, shown here, where you see the efficiency, like maximum power point drag, 50 hours. Once the light was on all the time, and the other phase, you were interrupting it, you were cycling it. So a bit more realistic, maybe kind of night. This was 6 hours to speed it up a little bit. And you can see there is, of course, a significant difference between two. These devices seem to have some reversible kind of effects regarding recovery. And then, of course, the real-world studies where these parameters fluctuate in time become even more interesting. And I want to show you now one study, which is admittedly a few years old, done at EPFL, where we tried to get the real-world profile into the lab. So it might have been still probably the first study, or I don't know whether actually others followed, where people really tried to put meteor data into the lab, emulate the weather, excluding other factors, like population related, atmosphere related. Here we just want to see temperature, illumination intensity, and their variation during typical days. And what we did, we took weather data. What do we have here? That's the weather data, exactly. In this case, we chose 2 days each from a weather station close to the sun and the year before. And we have both the illumination, intensity, and we have the temperature. And here, these are more the winter days. This is more summer, and here comes summer. Again, we put it into our aging setup. We use the temperature data to calculate a module temperature, accounting also for the wind speed. And there are models from silicon and thin solar cells, how you can do this and outdoor. We use this model to get a kind of more realistic module temperature. And we kept everything on the nitrogen. Devices were not encapsulated because NIP, cation devices. And we also use silicon solar cell, like heterojunction from Neuchâtel. I showed you already just before, temperature dependence, rather efficient ones as well, and to compare a little bit. And what you can see here on the top is how the power conversion efficiency kind of evolves. So it has some dependence on, so each of these, like, where one point is 1 day. The red point is kind of the average efficiency of this phase. So our perovskite solar cell started with around 18–19%, the silicon 22%. You see already silicon remains rather stable, whereas our perovskite had some fluctuations. Here again, you have the better data. And then we try to see whether we can analyze this data in a way. And we can, of course, try to do different things. What we can do is we can calculate like the energy that is harvested per day and compare it to what was expected. And to get the expected one, we need a pre-characterization so that we know initially the temperature and illumination intensity dependence of the solar. So this was just a pre-type before in the motivation. And we use this data, and then we could see in principle, now for the, you see here for the perovskite solar cell, there is very different scales compared to the silicon. Like the blue ones is kind of the variations. Now the silicon more or less kind of generally is a little bit, I think here in the winter months, it's a little bit higher because the lower temperatures and the standard reporting conditions. And then it depends a little bit also on the light intensity. But the perovskite solar cell are ideally stable, so you can see already degradation. When we have this data, of course, we can make interesting plots. We can, for example, like over this whole 24 days representing the year, we can plot color-coded here the efficiency versus temperature and light intensity in equivalence of sun. I have to say we were using LED and we didn't like attempt to also mimic effect. That would be another sophistication, but I think for single junction perovskite solar cell, not so critical. Good. And what you can see here for the silicon, in principle, one is the classical temperature dependence. The lower the temperature, the higher the efficiency, mainly because of the higher temperature. That's why, like a sunny, like spring day, usually we get like of installed capacity of photovoltaics in Germany. We get often the highest power. It must be already in winter, of course, we don't have many sun hours, but when we go maybe a cold spring day or something, is ideal. For the perovskite solar cell, that's a bit different. There is no clear monotonic trend. In our devices, it was mainly that interesting, you know, in this range, between 20 and 40 degrees, like around half a sun was the optimum. That was in this case good because this is where we get also most of the operation, like where we get also energy during having it installed in Central Europe. So because this is, I think, the next slide there you see like where did we harvest most of the energy. That is basically depends on the efficiency and like on the energy profile we have available during. So this depends, of course, where you install it. And we saw it is exactly like this, of course, for both very similar because the energy they bought was the same. And this is, of course, like not at very low temperatures and not at very low light intensities, but here more in the moderate range. And we have, of course, this correlation between intensity and temperature because the solar cells always heat up, even if there is strong wind for cooling. And of course, also general, of course, the ambient temperature during the middle of the day is higher than. Okay, as a last slide of this little study, I want to show you this one because I think this one is here very, very nice. And then I have to speed up to also conclude. So here we look at 1 day. And what we have here, the blue one is the silicon. You already calculate the efficiency, like so. Yeah, we have here like the temperature and here we have the intensity. So it was no cloud. I think it was really like kind of the ideal day. And the dashed lines here, this is what we would have predicted from the pre-characterization. So you see the silicon solar cell, of course, doesn't have like constant efficiency over the day. It decreases here at this in this case because the temperature is much higher. So that's the temperature effect. But you see, of course, we can nicely predict it. There was no anticipation. For the perovskite solar cell, that looks different because there's not so much temperature dependence, so the predicted value remains rather at around 20%, rather constant over the whole day. But the actually measured efficiency, so the solid line, orange one, is high in the beginning in the morning, and then it kind of decreases and stabilizes. And this is then already this effect of this reversible degradation, if you want to call it like this. And you can also have it if it's a cold day, that it takes time until it rises. And we try to quantify then from our harvested energy, you know, how much is due to this reversible effect and how much is due to permanent degradation. And then we got this plot. And how did we do this? Well, in principle, we checked, like, we try to find the maximum, or how to say in a better way, then we try to minimize the difference between predicted and measured one. And where it was minimum, we hoped that at this point, the kind of reversible effects were minimized so that we would only see the irreversible degradation. And with this, we would then, the equations are in this publication. And with this, we can then in principle calculate how much irreversible losses we have, and the rest we would have to do to reverse. And then we get this graph. And our solar cell was like degrading, especially there was some issues around the 15th day, and we lost. This is now always kind of referred to the energy harvested per day compared to what was expected by the initial characterization. So the blue one should kind of increase monotonically. And there is some variations because it might depend a little bit on how strong the reversible effects are depending on temperature and so on. And the reversible ones usually account here, these orange bars, for a certain share also. And I think the future such data can be used to analyze like more carefully, you know, trying to see what is the effect of temperature separately, what is the effect of light intensity. So now we have 5 minutes left. Of course, the question for the other origins of these like reversible effects, this I don't want to discuss here in detail. Now, very early it was proposed that there is some metastable trap states. That's maybe also like the first application where these reversible effects have been reported. Then later, an IDPFL led by Antonio, who will speak here later, it was suggested, you know, I was also involved, that it could be like slower ions. We had already the hysteresis attributed to maybe halide frequencies or other halides moving rather quickly in the seconds time, and maybe the other ion would take much longer time to finally stabilize. So this is like another suggestion. You can maybe refine this a little bit so that it's not only like, for example, how fast the ions move in the bulk, but also what they are doing at the interface. Studies very early already chemical reactions. This is what titanium pyrite group, titania perovskite interface. They're already suggesting that there can be reversible chemistry with the iodine. Also, like the ions, if it's not vacancy, maybe steel materials, you know, to penetrate charge transport layers, and then be stuck there for much longer time. And this can then really take hours, maybe weeks, until the system actually breaks. And we are now in winter tour. We are looking a little bit into this also, and we want to try to see on the nanoscale what is happening, for example, under light soaking. And we got some initial results, and they look interesting. So this is like a topography image, let's say, of the perovskite taken by AFM, and under light soaking, you can already, and sometimes you can really see like terraces, like for example, on this grain here, and they disappear. That should be the same again when you kept it under light. And interestingly, to some extent, I need to find this guy again, it should be here. It seems that even this kind of structural changes and the rearrangement somehow on the surface of this perovskite under light can be reversible. It's initial result, but just to show you our interest now is a lot on this nanoscale plus micron scale, also with luminescence, to see what is going on in this material. So I'm coming to the final remarks for the final 3 minutes. One point quickly I want to mention for the real world, which I didn't discuss now much, is what can happen if you have a serious connection of devices, of solar cells. We have to do this in the perovskite sintering technology. And I told you that the mobilities are not so high that we can make, like, also, let's say, big devices. So we want to have small stripes connected in series, make a module. And even if you make them big, at some point you need to connect them. And then, of course, if one cell is shaded in this series, then the current flow is interrupted. And it means the whole module doesn't produce doesn't deliver any power. Okay, you can say it can happen. But the issue is that at the same time, the other solar cells are all kind of at open state. They're not allowed to drive current. And then they bias the cell, which is in the dark, reversely, basically with the sum of their open circuit voltage. So you can reverse bias this. That's why only bypass diodes also for silicon, but you don't want this for each subcell usually. And this means the perovskite solar cell should also be a bit robust against it. And having already mentioned all these kind of dynamic effects happening already just between open circuit and short circuit, which is a small voltage window, and then you suddenly maybe want to apply minus 10 volts reverse bias. Yeah, that sounds a bit terrifying, maybe. But there is also already good results. It also again depends a lot on how the charge transport layers, for example, are designed. McGee group, and therefore that they try to apply here minus 10 volt reverse bias, and they could still have almost half an hour. Bias was still okay, not completely degraded. We're also working on this a little bit. We try to treat basically the whole transport layer spiral with some polymers, and we could also get like minus 10 volt applied in this like red device to monitor the current. Yeah, you see there is of course also some current flowing. The reference device directly died here at that point, and this device, interestingly, after reverse bias, it is strongly kind of degraded, but then you let it rest again, it recovers to the best. This line is after recovery, exactly recovers more or less to full performance. So there's of course the reversible effect, definitely you keep ions around, but it's also possible to not have it reversible. Okay, it's time for the end. So for final remarks, I think what is important, what we need to do, I think we don't need to necessarily try to always mimic, for example, the weather in the lab. It's a complicated experiment, but we can like do comparable tests like the ISO protocols. These are like standardized and have already lots of different kind of parameters that can be adjusted to represent temperature and so on. I think we should still gain more understanding what is happening by in situ and operando monitoring. There is another example where we saw this on the phase segregation. This I will now just directly skip, where we saw that in situ measurement, not only tracking how the phase separates by PL, but also tracking what happens in the solar cells simultaneously. We can, for example, say whether it decreases the open circuit voltage or not. In this case, it didn't do. Then we should do predictive accelerated aging. Here, very interesting study where they needed high temperature and to see some degradation, and then by some Arrhenius modeling this patient, they could predict then how long the solar cell will last under more real-world conditions. And at least last point, of course, I think we will have a talk today. We should do field testing as well of decent modules. Thank you very much.